Hey guys, welcome back to Akacademy once again. So in this particular lecture, we are going to start with one very important thing, that is carbene. Actually, we are starting with the reactive intermediate. So in this particular lecture series, we will understand what are carbocations and all about the carbocation type of reaction. And also along with that, we will understand carbon ion and carbene, nitrene, benzene, right, free radical. So these all uh, type of reactive intermediates we will study, and apart from this we will also understand the name reactions which are on the basis of in which actually these kind of reactive intermediates are getting formed, right. So these all things we are going to understand in this lecture series, so please watch all the lecture series. So what we are going to do in this, actually first of all we will understand the basic of the reactive intermediates, and after that first in the first step we will understand the basics, and after that we will move to the advanced level chemistry, and here in advanced level we will discuss the previous year questions, right, plus example from standard reference books like Clayden and Carruthers, right. So these all kind of examples so we are going to discuss in this case. First of all, let's understand about the basic of the carbene. So there are basically two types of carbene, you can see. The first of all, actually the carbenes which get formed in the reaction, they are of two types. The first one is singlet and the second one is triplet, right. And now let's see the characteristics of this singlet and this triplet. So what happens, first of all, let's see, if we have the singlet type of carbene, so in this we will have one x over here, one y over here, and here we will have one vacant orbital, and in one the electrons will be filled. And in triplet one we will have the same thing we will have, but here we will have one bond, two sigma bonds actually, and one electron in this vacant orbital and one electron in this vacant orbital. So now let's understand. So what is the first thing which you observe in this singlet? So we have basically two sigma bonds. So here we have two sigma bond, the first thing, right, and here two sigma bond is also present. And the second thing what we have, this is neutral species, right. So this is neutral and this is also neutral. And the third one is actually here what you can see, here we have one vacant orbital, but in this case we have zero vacant orbital, right. So here we have zero vacant orbital and here we have one vacant orbital, this one. And the fourth point which we can say is actually here we have 6 electron spaces. This is what, this is 6 electron spaces, right. So here we have this 6 electron spaces and this is also 6 electron spaces. The fifth point is 1, 2, and this is the first, and this is the second, and here we have third one, and here we have this fourth one, and here we have this fifth one. So let me write like this. The sixth point which we can say, because 6 electrons are here, because now let's see, 2 electrons is over here, right, and 1 electron is over here. So this is the third one, and here we have this one more, fourth, and one of this y and one of this x, right. So total 4 plus 2 means 6 electron is there. So that's why this is what electron deficient species. So we can call it this can be called as electrophile or the Lewis acid, right. So here we have 6 electron, and if I talk about the shape of this carbene, so what is the shape of this carbene? So this is a kind of bent structure we will have, just like the water, right. And here the hybridization, if I say, so here we will have sp2 kind of hybridization, right. So and in this case what we have here, in the fifth point if I talk, this also have 6 electron, right, this also have 6 electron in this case. Actually let's first understand about the singlet and then we will move to the triplet. So here what we have, here we have the bent structure, right, in this carbene we have the bent structure. And the next point which we can say is actually the electrons are occupied, right, electrons are completely filled in one orbital. So there is no unpaired electron. So if we don't have any unpaired electron, so in that case what happens actually, so this cannot be detected by the ESR or EPR, because in that case actually we require at least one unpaired electron. So that's why this cannot be actually detected by the ESR or EPR. EPR, right? The next point which we can say is, here because the electrons are already paired, so this will be diamagnetic in nature. This will be diamagnetic in nature, right? Now because two electrons are getting filled in only one orbital and one electron is still incomplete, so this is not going to follow Hund's rule. Hund's rule not obeyed. Please remember, in this carbene, Hund's rule not obeyed, right? And if I talk about the next one, so what we have, if I talk about the spin multiplicity of this singlet carbene, so in that case we have formula 2 summation s plus 1, right? So here what we have 2, because the electrons are, both the electrons are in one orbital, so that's why the spin will be different. So in one case we will have plus half and in another case we will have minus half, right? So plus minus half will become 0. So here we will have 2 into 0 plus 1 and this will become 1. So here we are getting 1, right? So that's why this is called as singlet carbene. And we will come to the another thing also about the repulsion and so many things we are going to explain. And first let's understand this one. Now here we had about the band structure, here we will have, right? But here the carbon will have sp3 hybridization over here, right? So carbon will have, sorry, not sp3, but carbon will have what? Sp hybridization. Here in this case the carbon have sp hybridization, and if I talk about the shape and structure, so it will have linear kind of shape, right? And after this, if I say, so here in this case, because you can see here we have the unpaired electrons, so this can be detected using the ESR or EPR, right? ESR or EPR, this can be detected using the ESR or EPR spectroscopy. Got it? Because what is the reason? Because we have the unpaired electron, and this is also unpaired, right? Now, and this is also the neutral one, we know already, because two electrons, you can see they are actually filled in the different orbitals, in the p orbital, but in different orbital if I talk, right? Like in this case the two electrons are filled in one orbital, so this is also called as biradical. This is also called as biradical. If I talk about the spin multiplicity, so in that case we have 2 summation s plus 1, because two electrons will have the same spin, either both will have plus half or both will have minus half, right? So here 2 into, what will happen, the spin summation s will be equal to 1, plus half or plus half will be equal to 1, right? So 2 into 1 plus 1, here we are getting spin multiplicity as 3, so that's why this is called as the triplet carbene, right? And this follows Hund's rule. Hund's rule is obeyed by this one. Got it? I hope you understood up to this much. Yeah, so this is about the basic thing about the carbene, and now let's discuss certain more things about the carbene. So where we will discuss about the actually repulsion and all, actually what kind of carbenes are more stable actually, right? So these all things we are going to discuss. So first of all, in singlet carbene, if we talk about this singlet carbene, so if we have this carbon, so here in this carbon what happens actually, already we know that the electrons are filled in only one orbit or one orbital, right? Like this. If I talk about the bond angle of between these two H, so what happens, because here we have two electrons and the repulsion between this electron and this hydrogen will be higher than this one. If I talk about this one, so here what is happening, here what we have, here we have two electrons, this is triplet one, right? Because we have one electron over here, so repulsion will be less over here, and here the repulsion will be higher one. So if the repulsion are actually higher one, so in this case the bond angle will be equal to around, it will be in the range of 100 to 110. But if I talk about this one, so it will have bond angle 130 to 150, like this much degree. Got it? The reason is why we have this 100 and 110 here. The reason is actually what is happening over here. Please try to understand. Here we have this electron pair, and this electron pair is actually, this will repel this hydrogen much. That's why this angle will be reduced. So that's why we are getting 100 to 110. Here we have less repulsion, so that's why this bond angle will be higher as compared to this one. So here we are getting 130 to 150, right? Now let's talk about the stability of the carbenes. What happens in case of stability? If I talk about the stability of the carbene, in that case, here you should understand some basic things regarding the stability. Actually, the singlet carbene which is formed over here, we have some kind of singlet carbene like this. So this singlet carbene, which you can see over here, at least here, if I say here two halogen groups are attached over here, right? If the halogen groups are attached over here, so because of back bonding, what happens? Because of back bonding in this case, this chlorine will donate the electron to it, and here this is going to form something like this. Here Cl positive charge will come in onto this one, right? Because Cl has donated its electron to this carbene. So positive charge will come, and that is the actually reason why this carbene will get stabilized, right? So this is the reason actually why this carbene will get stabilized, right? This is the first region. Either actually what happens here, we should have back bonding, that is the first case. And the second thing here, what happens if suppose we have one polar solvent. If we have polar solvent, let's say we have this water molecule, right? So this water molecule, this oxygen will actually, this will try to stabilize this carbene, right? However, the carbenes are actually formed in any kind of reaction, but this is not a complete reaction, right? This is not a complete reaction. Formation of carbene is not a complete reaction. Once the carbene will be formed, and after that either any nucleophile or any reagent will attack on the carbene, and that is going to form the final product, right? And that will definitely form the final product. So what I am trying to say you, the carbenes can be stabilized using the two things. The first thing, actually, if we have any group attached with the carbene which can donate the electron. For example, if I say we have this NH2 over here, right? NH2 over here, Nr2 over here, Nr2 over here. But if I say we have R over here and R over here, so what will happen in this case, right? So this carbene actually will be very less stabilized, and this won't try to exist as a singlet carbene. This will get converted into triplet one, right? If we have any electron donating group, right, where the electron pairs can be given to this carbon, right, this electron deficient carbon, like Cl over here, oxygen over here, nitrogen over here. So that in that case we will have singlet carbene. But if suppose if this carbene is connected with some other groups where we do not have any kind of lone pair on this particular atom, so what will happen in that case? That will exist as a triplet carbene. So when the carbenes are actually existing as a singlet and the triplet, the first thing, if we have polar solvent, and the second thing, if we have the groups which are attached with this carbene, and that groups actually can donate its electron pair to this electrophilic carbon, in that case we will have singlet carbene. But if suppose if we have gaseous medium, right, if we have gaseous medium, and also we have non-polar, here we have, if suppose we have non-polar medium and gaseous medium, and back bonding is absent, back bonding is absent. So in that case only triplet carbene will be formed, right? In that case only triplet carbene will be formed. And one more thing is there, if suppose steric effect is also applicable in the formation of carbene and the stability of the carbene, steric effect, right? So what happens if suppose if we have any carbene, let's say here I have this something very much complex one. For example, if I am taking this nitrogen, and here we have this carbene like this, and here what we have, something like this, a little complicated one. So here what you can see, here we have this bulky group, right? Here we have this bulky group. So in that case this carbene will always exist as triplet carbene. So carbenes, actually in that case we have the steric or bulky groups that are attached with at the adjacent position, right. So in that case the carbene will always exist as a triplet carbene. So in that case that won't exist as a singlet or the triplet carbene, right. Now let us understand some more thing regarding the stability of the carbene, and we will also discuss certain more things. For example, if I say we have a carbene something like this, if carbenes are how actually formed, if I remind you about the Rearrangement reactions, what was happening over here, we had this CH, Cl, 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 right, and one base, let's say we have this KOH, and this base was abstracting the proton from here, and the formation of this kind of species was taking place, and after that what happens, actually this Cl will get removed and we have the formation of this singlet carbene like this. We had the formation of such kind of carbene in that case. But if I say, let's write 2-3 reactions and let's try to understand what kind of carbene will be formed in this case. For example, if I say we have CH over here, right, and here we have what, Cl2, and here we have this Br, right. So in this case what will the carbene formed if I am treating it with base OH minus, right. If I take I, we have here we have this CH, and here we have this Br, and here we have this Cl, right. So which group will remove over here? If I take, we have this ICH, and here what we have, F2, right. So in this case what will be the reaction, and which one will be more stable, we also have to discuss that one. For example, if I say we have this CHI2Cl, so in this case what will be the reaction? So let's write the product. First of all, you try to write down the product and then I will explain. In this case, because Br will be easy to remove in this case, so here the formation of CCl2 will take place, right, like this. And in this case, because I is quite bulkier, quite heavy and very good leaving group, so I will remove, and here we will have C, here we will have this Br, and here this Cl. In this case, this I will remove, so here we will have this F and this F, right. In this case, this I will remove, and here we will have one Cl and one I, like this. So all are carbenes. So this is the kind of formation of carbene takes place. I am coming to that point, how the carbenes will be formed, and we will discuss a lot of examples regarding that. But here the question is, which carbene will be more stable? For example, if I say we have this one, if I say we have this one, and if I say we have this one, and if I say we have this one, right, fluorine, chlorine, bromine, iodine, right, fluoro, chloro, bromo, iodo in this case. So in this case, because here what we have 2p kind of overlapping in this case, and 2p kind of back bonding, so that's why this will be more stable. Then this will come, and after that this will come, right. So this CF2, which you can see over here, so this will be more stable carbene. Got it? The reason is because 2p kind of back bonding is there, so 2p kind of back bonding is quite more special, and that will be actually the stronger one. So that is the reason why this carbene will be more stable, right. So I hope you got up to this much, and now in this particular video let's understand how we can form the carbene, because that would be very interesting to understand. So in the formation of carbene, actually the very important thing which we have is the formation of diazomethane. So what this diazomethane do, and what about the reaction of this diazomethane? We will understand so many things regarding this diazomethane, but in this particular video, please be patient, and we will discuss about this diazomethane, and we will discuss many reactions, and there definitely you will understand. And apart from this all reaction series, so definitely in the reaction mechanism and all, so many kind of reactions you will see of this diazomethane, right, or in the reagent part also. So you can get this one, because there we will discuss about the all separate reagents, so many things, and there you can get the separate questions and everything, each and every detail about this diazomethane. This diazomethane, if we use actually, so this is kind of explosive material, right. If this is the explosive material, so in that case it becomes very much difficult to handle it. So in the reference book, what kind of example you will see how we can actually find out the diazomethane, and how we can actually generate this diazomethane, right? So what happens in this case? Here what we have? Here we have something like this, which you can see in this case, this compound, right? And this compound, when this is treated with the base, we have this NaOH. So in that case, the formation of diazomethane can takes place, right? So here, how the mechanism will proceed, I am coming to that point as well. So here what we have? Here we have this Me and this N and this O, right? And here in this case, what you are getting, this CH2 and this N plus and this N minus. So from this part, actually we will get this diazomethane. Same here over here, from this part we will get this diazomethane if we are treating it with base, right? So now let's understand how we can actually generate this diazomethane. So here we have this OH minus, right? So this base will attack over here. If I talk about this reaction, so what will happen here? This base will definitely attack over here, which you can see in this case. Here we have this S double bond O, right? So here this OH minus, if this will attack at this position, so what will happen in this case? This bond which you can see over here, so this will shift over here. This will shift over here, and this complete, what you can see, this complete part. Actually here double bond O, one more double bond O should be there, right? So this will get removed, and here we will have, from this we will have, here this bond will shift over here, so this bond will again shift over here. So here we will have this CH3 and N, double bond N, single bond O minus, and here on this nitrogen, here sorry, 3 bonds are already there, so no charge will be over here, right? So we got this one, and after this what will happen? If I use the ether, right? If suppose if we have this ETOH or the water molecule, so this will abstract one proton from here. So here we will have CH2H like this, and double bond N, and here we will have this as OH like this, right? So we will get this one. After this, if again this base abstract this proton, so here we will have this CH2 minus, right? And this minus will shift over there, and this will shift on this carbon. So this will become N minus. So here what we will have? CH2 double bond N, here we will have single bond N minus, and here we will have this as, right? Here what we have? This as OH like this. So if the lone pair of this electron shift over here, so this removed as OH minus. So here what we have? This CH2 double bond N, and here what we have? Double bond negative and this positive. So this is the structure of diazomethane. This is very important in this reaction, so that's why we are discussing about this, and this is the mechanism how you can get this one diazomethane, right? Now let's understand certain more things and how we can generate this one and what kind of reaction will take place. Actually all the examples which you are seeing over here, we have been actually taken from the standard reference books, right? So here if we are using this diazomethane, so first role of this diazomethane is to actually remove this acidic proton, and instead of this acidic proton here introduce a methyl group, as you can see in this one. And here this proton, because this is a phenol, so this proton is acidic in nature, right? So that's why this will be replaced by this methyl. But if I talk about a normal alcohol, so in that case will it reduce? No, right? So it won't be it is not going to introduce the methyl group over here. So here in this case no reaction will take place if we are using the diazomethane. However, this is a very active one. But if I use HbF4, right, this one, or if I use HNu, so in that case this reaction will proceed, and in case of the alcohol as well, so this hydrogen will be removed from here and methyl group will be introduced. So it means that it requires a catalyst or the photon to proceed the reaction. For example, if suppose if we have this one CH2N2, if I am treating it with this one, so here the hydrogen which you can see, because this is the acidic hydrogen, right? Here what we are doing, actually we are doing the selective methylation in this case, right? Because this hydrogen is acidic in nature, so that's why here we will have CH3. I am writing like this only, right? Because I am not going to draw the complete structure. So this OH will get converted into this OCH3 in this case, right, in the first step. But if I using this CH2N2, so because you can see, because these two OH are actually alcoholic in nature, right? So in the first step they won't get here, this hydrogen won't get replaced, right, and CH3 won't come over here. But in the next step, if we are using this HbF4, so in that case here what will happen, I am writing only this one. So here we will get only this OCH3 and OCH3, and apart from this OCH3 will remain as it is, right. So this one we will have. Now the question is how we can generate the carbene from this diazo compound. That is also very important thing, right. Now let's understand how we can generate actually this. If we have something like this, then what happens actually, because this negative charge you can see this will shift over here, right, like this. If this is getting shifted over here like this, so what else can takes place over here, let's understand. So this will shift over there, right, not over here, I can say this will shift over here and this will shift over here. So this will become O minus RC, here it will become O minus, and here what we will have, we will have this CH, and here single bond, here double bond, and here N, here we will have this triple bond like this, and here positive charge on this nitrogen we will have, right. This is the first thing. And after this, once it come over here like this, so it will come back again to its position like this, and this bond which you can see over here, so this will get broken, and we will have something like this, plus N2 will get removed. So this is the carbene how which we will get in this case, right. And this thing we are also going to understand in the Wolff rearrangement reaction, right. Actually this process is called as the Wolff rearrangement. So what happens if we have this R over here, so what does this do, this R actually, because this is electrophilic carbon, right. So what happens in the Wolff reaction, let's understand it over there, over here only. So here we have this electrophilic carbon, right. So we got this one, so this R will get migrated over here, and here we will have R C like this, right, and this complete bond is getting shifted over here. So R C, here we will have this C double bond, this double bond O, like this. Getting the point? So here this R will migrate over here, right. So once this R is migrating over there, so we will have something like this ketene is actually formed in this case, like this, and here one hydrogen is also present over there, right. So this is called as ketene, right. Once we will discuss about the nitrene, so in that case actually what happens, isocyanate is formed. Here there is no much difference between the, if you will see about the carbene reaction and the nitrene reaction. So if I take something like this RC double bond O N, so in that case this R will migrate over here, and this will going to form R N. Here what we will have, so here what we will have, the positive charge on this carbon, right. So here positive charge on this carbon will be generated like this, because this group has migrated from here to there like this. And after this what will happen, we can have isocyanate in this case, right. So isocyanate R and double bond C double bond O, isocyanate. This we will discuss in the Carruthers rearrangement, right, and this we will discuss in the Wolff rearrangement. I hope you understood up to this much, right. Now let's understand the formation of the carbene, actually how the formation of this carbene will take place. So this is the part 1 of this lecture series, and in the part 2 we are going to discuss some more reactions and about the formation of the carbene, and after that we will discuss about the reactions of the carbene in detail, right. Let's understand.